Okay, thank you. Welcome back. I'll begin by sharing what we'll be covering in the remaining months, if time allows us. So far, we are looking at groups. After that, we're supposed to look at rings, then fields or finite fields, look at polynomials and graph theory. All of them, we'll be applying them in cryptography. After that, very fast, we'll look at linear algebra, where we'll be looking at vectors and matrices, systems of linear equations, eigenvalues, eigenvectors, and applications in cryptography. Then look at, of course, application of linear algebra in elliptic curve cryptography, After that, of course, we must that these topics will be in the order they appear in. Then we look at hash functions, we look at SHA-256, we look at digital signatures, we look at homomorphic encryption, then revisit public key cryptography while looking at RSA and define, then look at elliptic curves, look at elliptic curve digital algorithms, and then implement elliptic curve digital signature algorithms and other cryptographic algorithms using Rust. And then we look at zero knowledge, where we'll be looking at ZK snarks and look at ZK stacks and then ZK rollups, and of course their applications. We can also look at symmetric key crypto systems, AES and DES. Then from there we go to post-quantum cryptography. And under that, we look at lattice-based cryptography. That is what I've listed here, the post-quantum crypto systems. The post-quantum crypto systems, we look at that. Lattice-based, look at code-based, look at multivariate quadratic equations, look at hash-based cryptography. And of course, we look at algorithms, post-quantum algorithms like the Shor's algorithm and Grover's algorithm. Then look at post-quantum digital signatures and post-quantum zero knowledge proofs. So, of course, we will have already looked at zero knowledge proofs, the ZK snarks and ZK stacks. But now we bring in how do you customize it so that it can now do also the post-quantum cryptography. That is our zero knowledge proofs. We do them in post-quantum way. And then if we have time, we also are supposed to look at probability and statistics for blockchain. And then look at, time allows us again, we can even look at Ethereum and smart contracts development, where we can introduce Solidity and then look at introduction of smart contracts and smart contract deployment. Then Ethereum virtual machine, if time allows us. So that is what, that is the plan for the remaining months, for the remaining lectures. Of course, we already done this our 51 lecture. So where we are today be finalizing our new on groups, where I'll be looking at homomorphism in groups. Then we shall now begin on rings and then go to finite fields. But the rest of the topics from topic 2 going down, we may cover them in order because like Not much of them, not most of them are dependent on the other ones. So where we have one dependent on, we shall do the one that is prerequisite first. Shall do the prerequisite, then do the other one first. I believe that after covering this topic 2, then we can begin attacking these other topics. We can begin from hash functions and so on, digital signatures as we go down. So that is the program. Of course, I will share that program so that you can also have it. Okay, so we want to begin our lesson today. Just want to share it. Let me see where it is first of all. Okay. So today we look at our lecture 51. And as I said, there's a continuation of groups. So tackling almost the last thing on groups. The good thing is that once you understand groups, and then it will be easier for us to understand the rings and then fields as we progress. So what is a group homomorphism? So I've defined that as a function between two groups that preserves their group operations. We know what group operations are. The group operations could be either addition or multiplication, not all of them at once, one at a time. So we are saying that a group homomorphism is just a function between two groups. So where you have two groups, and we might combine these two groups by either addition or by multiplication. That is why we say operations. That means operation is addition, then that operation will be preserved. If it's multiplication, and again, it will be preserved. So I've said it's a fundamental notion in abstract algebra and has numerous applications in cryptography, number theory, and also topology. But our interest especially would be the application in cryptography. That's where our interest is. So we'll be looking at this group, a group of morphisms, and how do you apply them in cryptography, especially in securing data, securing information. So now the formal definition is here for group homomorphism. So I have two groups, group G and group H. Now the operation is this. This operation, I've used this just to mean general operation. It could mean addition or it could mean multiplication. Don't take it to be multiplication because it's a dot. So it's not multiplication, this one. I've used it to mean either addition or multiplication. And again, for this other group, I've used this other operation to mean either addition or multiplication. So it does not mean it's multiplication or what, but it's any of them. So it depends on whether the group is additive or whether the group is multiplicative. Now, so that is about the operations. I hope from the very start we know what those symbols mean. So this is a group G with this operation and group H with that operation. So the function phi, this function phi, that maps G to H, the function phi mapping G to H, this is how I read it, this is how it's read. This is phi. The function phi mapping G to H is called a group homomorphism. If for all A and B, these are elements in G, if for all A and B in G, the following condition is holds if it's satisfied. if this operation is satisfied, we say that phi, therefore phi, this phi is a group homomorphism. So phi is the function, phi is the function. And I say that this function must preserve, it must preserve the group operations. So phi is a function. And so it, therefore, it's what we are calling a homomorphism. This phi is the homomorphism. And I've said the homomorphism, phi will be considered to be a homomorphism if for any two elements in G, phi of AG. So remember that this could be either addition or multiplication. So if it's addition, then we are talking of phi of A plus B. If it's addition, we'll be talking of that. But if it's multiplication, again, we'll be talking of phi of A times B. So that is, I want to understand that from the beginning. So that means phi of these two elements, you can now distribute. You can distribute phi inside. And when you distribute phi inside, you get phi of A and then phi of B. So this operation should be the same as the operation here. That's what it means by preserving the group operations. So when we say that phi preserves the group operation, what we mean is that the operation that was here should be the same operation that is there. The operation that is there. For instance, if it's addition, and if A is 2 and B is 3, then we are talking of phi of 2 plus phi of 3. Plus phi of 3. That is if this was addition. But if it's multiplication, then what we mean is that phi of 2 times 3 be the same as phi of 2 multiplied by phi of 3. So that is what we mean by group homomorphism. Group homomorphism. admit these others. Okay, it's okay. Now, so I hope the definition is clear. I just want to explain a few concepts on this definition, especially on the notion of preserving the operation, the group operations. I just want to do some explanations there, and then we look at examples to assist us understand. Now, so what does this equation imply? I've said that this equation implies that the structure of the operation in G is preserved in H. So that means that if the operation in G is addition, then the operation in H will also be addition. And if the operation in G is multiplication, then the operation in H will also be multiplication. That's what it means. So that's why I've said that is the result of multiplying two elements A and B in group G, when passed by this homomorphism to H, when it's passed to H, when this result is passed to H, then it will be equal to multiplying the images of A and B in H. Now, so this is the image. This is the image of A, and this is the image of B. That's what it means. So I had A and B. I had element A and B, and then I carry out this operation. I do the homomorphism on these two. The operation, if the operation is addition or multiplication, that is okay. But now what happens is, what I get is the image of A with the same operation that was in G. If it was addition or multiplication, that operation, then the image of B. That's what we get. Now, so element A is in G. Element B is in G. But the image of A is in H. And the image of B is also in H. That one, you get it from here. get it from here. So the elements A and B are from H. No, are from G. But the images are in the second group, which is H. So that's why I get the images. So again, just as emphasis, I've said that phi then maintains the rules in the target group. It maintains the rules. That means, that again means is that if the original group, the operation was addition, that rule will also be applied in the target group and so on. Good. That is about the definition. And I've said that what I used in the definition was general. So it could mean either multiplication or addition. It could mean either of the two. And let's look at the basic properties of group homomorphism before we look at examples. Now, the first property is that of preservation of the identity element. That is, now I've used this to mean the identity in G, just to avoid confusion, and I've used this to mean the identity in H. So if this is the identity in G, then phi of this will give us the identity in H. Will give us the identity in H. So remember that what we're getting in H is the image of the element in G. So what we're getting in H, so what that means, the image of this element E, its image is this. So what that means that the identity element is preserved. The identity element is preserved with the same identity element. Then the other thing that is preserved is the inverse, preservation of the inverse. And what that means is that if G is an element in G, then phi of that in the inverse of G, phi of the inverse of G will be the same as phi of G inverse. So those two will be the same. So there's not much here actually. It's just the same thing, but now it's just the bracket that has changed position. Commutativity, we had talked about commutativity earlier. So what this means, if we have two homomorphisms, then we can have them being commutative. We have two homomorphisms. Like if this is one homomorphism, phi, and this is another homomorphism, mapping the same groups, mapping G to H, and also this one mapping G to H, then their composition, phi composition, this will also be a homomorphism. It will also map G to H, and it will also be a homomorphism. Good. Let's just look at examples so that we understand what a homomorphism is. But I had already know what a homomorphism is, so just want us to do examples. Let's go back to the definition and look at it, and then we proceed to examples. Now, A and B in this definition, they just mean these are elements of a group. Those are elements of a group. So supposing the group is our Z3, and then we know what the elements here are: 1, 0, 1, and 2. These are the elements. So you can choose any two elements from here. That's what we mean. If you choose any two elements here, let me say you choose 1 and 2, and this is an additive group. This is an additive group. And suppose we have another group also. Want to call it okay, we can just use this one group to illustrate what we mean by homomorphism. So what we mean is, if you pick any two elements, let me say you pick 1 and 2, and this is an additive group. So we expect that the answer that we get, the same as phi of 1 plus phi. That is the answer you get. And of course, for us to do this example, there could be several definitions. We'll be given several information about this group so that we now do it completely. But basically, that's what it means. So you have a group, pick two elements, apply phi to them, and see what you get on the right-hand side. Let's look at this example. This example says, verify that phi mapping R to R. R is just a real number. These are real numbers. Mapping real numbers to real numbers. Okay, let me now read the question. Verify that phi mapping R to R defined by phi of x is 2x is a homomorphism. So they have given us the definition of phi. They're telling us that if phi maps an element in this group, that element will be mapped to 2 multiplied by the element. It will be mapped to twice the element. Let me just show you an example. What it means, supposing I'm mapping this real number 2. This real number 2 should be mapped to its double. So it should map to 4. That's what it is. Because this is x. So x just multiply x by 2. So if I map these 2, it map to 4. That's what this definition means. That if I was to map 3, then it will be mapped to 6. So that is what this definition means. But now the question is, show that it's a homomorphism. Show that it is a homomorphism. So I was just assisting us to understand what the definition says. The definition says, verify that phi mapping R to R defined by this is a homomorphism. So for us to verify, what we want to show, this is what we want to show. To show that it's a homomorphism, that's what we want to show. That's what we want to show. So I've said to verify that this defined by this morphism, we are required to check if it preserves group operation of addition. Because this is an additive group. This is an additive group. Remember that if it's multiplicative, it's supposed to have a star. If it's multiplicative, it's supposed to have a star. Remember that. We have already looked at that. So since it has no star, it's an additive group. So we want to see whether the group operation of addition is preserved by this phi, which is defined by this. So we want to see whether it preserves the group operation. So just use our definition. Our definition says that if you have 2 elements and apply phi to them, then the result that you get is this. You get this result. So for us to verify, therefore, we shall compute the left-hand side and then compute the right-hand side and see if the right-hand side equals the left-hand side. Let's begin with the left-hand side. Left-hand side, phi of A and B, of A plus B, by this definition here, is supposed to be 2 of A plus B. By this definition, because we've said that if you have an x, it will be mapped to 2 times x by the definition. If you have an x, it will be mapped to 2 times x. So what about if you have A plus B? Why will it be mapped to 2? So A plus B, therefore, by that definition, will be mapped to this. But this one, you can open this bracket and discover that it's the same as 2A plus 2B. So the left-hand side has given us this. The left-hand side has given us that. So we want to check whether the right-hand side also gives us this. If the right-hand side gives us this, then it means that phi defined as above is a homomorphism. So that is what we want to check. So let's check the right-hand side, this right-hand side. Now the right-hand side, if I have phi of A, by this definition, it will be mapped to A. What about phi of B? By this definition, it will be mapped to B. So what is phi of A plus phi of B? So this will be 2A plus 2B. So this then confirms that the left-hand side and the right-hand side are the same. And since they are the same, then we say that phi above, defined above, is a homomorphism. Is a homomorphism. So I want to know what the homomorphisms are, first of all, by doing examples before we go to applications. Now, so that means that phi is there for homomorphism. So let's look at another example, see what is homomorphism. Another example, determine whether this phi mapping Z to Z6 defined by this mod 6 is a homomorphism. So the mapping Z, you see Z, these are integers. Z, these are integers. Let me just remind you what integers are. Integers are elements, all the negative elements we know, and all the positive and negative numbers we know, whole numbers. For instance, dot, that means continuation. So like -4 is an integer, -3 is an integer, -2 is another integer, -1 is an integer, 0 is an integer, 1 is an integer, 2 is an integer, and so on. And so on. So those are integers. What about Z6? Z6 are also integers, mod 6. These are integers mod 6, but this one is 0, 1, 2, 3, 4, then 5. This is what we mean by Z6. Those are integers mod 6. So the question is, we have this function. This function is mapping these elements of Z, mapping the elements of Z to these elements. So we want to map the elements of Z to these elements. And the definition should be that every element of Z that you map, you map it to n. If you are mapping n, map it to 2n. For instance, if you are mapping 2, if you want to map 2, map it to 2 times 2. If you want to map 3, you map it to 6. That's what this definition. So what we are doing is this. What we are doing is we have this set. This is our Z. It has all these elements: -4, -3, negative, all the way 1, and then 2, and so on 0. And you are mapping to Z6, which only has 0, 1, 2, 3 up to 5. So the question is -4. Where will -4 be mapped? -4 is supposed to be mapped to 2 times -4, which is -8. But when it reaches here, you reduce it mod 6. Mod 6. You reduce it mod 6. So the question is, where will it be mapped to? So you just add this to that, you get -2, and when you add again, you get 4. So that means this -4 will be mapped to 4. -4 will be mapped to 4. Up to 4 there. What about 2? 2 will be mapped to 2 times 2, which is again 4. What about 3? 3 will be mapped to 3 times 2, which is 6. But 6 mod 6 is 0. So it's mapped to 0. What about 4? 4 mapped to 4 times 2, which is 8. 8 mod 6, that is 2. So that's what you are doing basically. That's what you are doing. You're mapping elements of one group to the elements of the other group. Mapping elements of one group to the elements of another group. That's what you are doing. Now, so we want to map the elements of Z to Z6, and the definition of phi has been told. We've been told that phi would map an element in Z to 2 times that element. So if the element is 3, it will be mapped to 6. If the element is 4, it will be mapped to 8, and so on. Now, so we want to show that it's a homomorphism. We want to show that that is a homomorphism. I hope everyone has understood what we are doing, what this means. This is just a mapping. We're mapping elements of one group to another group. The term that I used at the beginning was image. The word image is the one I used at the beginning. So, for instance, what is the image of 2? What is the image of 3? So supposing there is a mirror. So what you are saying is, if this is the object, then what is the mirror? Or what is the image? So, for instance, if you have 2, if 2 is the object, by this definition, it will be mapped, its image will be 4. That's what it means. About 3, by this definition, so 3 is the object, and then the image will be 2 times 3, which is 6. But now, under mod 6, 6 will be 0. 6 will be 0 under mod 6. What about 4, for instance? 4 will be mapped to, its image will be 8, mod 2, mod 6, that will be 2, and so on. So that's what we are looking at. Yeah. That is what we mean by mapping. But now, what about homomorphism? Homomorphism, we are saying, suppose you take 2 elements, these 2 elements, for instance, 2 plus 3. We expect that the result will be the same as the image of 2 plus the image of 3. That's what we expect the result to be. Now, so what do we just want? We want to, for instance, check the left-hand side. The left-hand side, of course, this one you can even add and you get 5. There's no problem. You can even add and get 5, and then the image will be 10. Mod 6, that is supposed to be 4. But let's see. Let's see, by this definition, phi of 2 plus 3 will be the same as 2 into 2 plus 3, which is 10 mod 6. Mod 6 is 4. So the left-hand side has given us 4. So you may want also to try the right-hand side and see what it is. So the right-hand side, we begin by phi of 2, for instance. When we check phi of 2, by the definition given to us, it's supposed to be 4. Let me admit this first. And then you also check phi of 3. By definition, that is supposed to be 6, mod 6. Now, what about the sum of these two? The sum of these two is 4, the same as the one we had gotten earlier. So dealing with homomorphisms is not difficult. It's very easy. Once you understand what it means, once you understand that we are just mapping elements of a group to another group, and we are saying that if the operation is addition, that operation must be preserved. If the operation is multiplication, again, it must be preserved. And once you know the definition of a homomorphism, it becomes very easy. So when you talk about, for instance, homomorphic encryption, then this is an encryption that copies the behavior of homomorphism groups. When you talk of homomorphic encryption, for instance, then we'll be looking at encryption that preserves, that copies behavior of homomorphic groups. So that supposing you have two groups and you are doing some operation on those one group, to come up with another group, elements of another group, and then the operation must be preserved. Can you can still hear me? Is that okay? Because I don't know whether I have the network. Okay.
Yes, we can hear.
Oh, thank you. Because I was trying to admit others here, but every time I tried to admit, I thought there was a challenge in a network. Because I've been trying to admit them, I can just see joining, and they don't. So I thought maybe a network, maybe it could be on the other end. Now, so let's now do this question. This question is, the question was, determine whether these are homomorphism. So I just used as an example to show that, but now I want us to do the question. The question is to determine whether these are homomorphism. We want to check whether it preserves group operation, which is addition in this case. All these groups are additive groups. So we want to see whether it preserves. So this is the definition. This is a definition of a group homomorphism. So we'll check the left-hand side and see whether it equals the right-hand side. So the left-hand side is this, and the definition was an element, this is an element of that group. So this element should be mapped to twice the element. So that is the definition. So this element should be mapped to twice the element. So this element A plus B, element A plus B. So we treat it as one element. So it's mapped to twice, mod 6. And when you distribute these two, this will be the same as 2A plus 2B mod 6. Now let's also check the right-hand side. The right-hand side, phi of A, first of all, will be mapped to twice of A, and then phi of B will be mapped to twice of B. And now, what about the sum of phi of B? The sum of phi of A and B will be this 2A plus this 2B, mod 6, both of them, which again gives us the same result as the one we had obtained earlier. So it means, therefore, phi as given to us is a group homomorphism. Is a homomorphism. Phi as given to us, since it has fulfilled that condition, is therefore a homomorphism. Okay. And now I want to check multiplicative group. The same group we had phi mapping R to R, but this time we want R to be multiplicative groups. So we remove 0 from them. We remove 0 from them by this star. By this star. This star means you remove 0. So when you remove 0 from real numbers, you remain, the only identity element you remain with is 1. Now we want phi to be defined as this, that every element in R is mapped to its square. Every element in R is mapped to its square. For instance, The image of 2 will be 4. The image of 3 will be 9. The image of 4 will be 16. That's what this definition means. That an element in R would have its image being the square of that element. Of course, this part was not necessary, but I just used it to tell you, to remind you that when I talk of R star, I mean R without zero. I mean R, this symbol here means minus. This symbol here means minus. This one. So I mean R star is just R minus 0. That's what I mean. But of course, that part was not necessary, since at this point we already know what R star means. We've seen it severally. Whenever there's a star, of course you know that. So you know that, for instance, if we have Z star 6, then we just mean elements from 1, 2, 3, then 4, 5. But when you just talk of Z6, then we mean we include 0. So when you include 0, it becomes a group under addition. When you remove 0, you consider it as a group under multiplication. When you remove 0, it becomes a group under multiplication. I don't mean this Z star 6. I don't mean that Z star 6 is a group. Z star 6, of course, would not be a group. Z star 6. If you remove 0, only 0. If you remove 0 and have this will not be a group. Because for it to be a group, if you want Z star 6 to be a group, then you should define Z star as a set of elements which are relatively prime to 6. A set of elements which are relatively prime to 6. So it becomes a group now. It becomes a group. So it depends on your definition. It depends on how you define your group. For instance, in this case, I've defined Z star to be a group without 0. So when you just remove 0 alone, Z star 6 does not become a group, because some of the elements here would not have inverses. Some of these elements will not have inverses. For instance, the inverse of 2 is not there. You cannot find an element in this set which, when multiplied by 2, gives you 1. That element is not there. 3 has no inverse. There's no element which multiplied by 3 would give you 1. 4 has no inverse. The only elements with inverse are 1, 5, and 1. The inverse of 1 will be 1, and the inverse of 5 will be 5. So that 5 times 5 gives you 1. Mod 6. 5 times 5 is 1, mod 6. 1 times 1 is also 1. 1 times 1 is also 1, mod 6. So that means, again, 1 is its own inverse. But 2 and 3 have no inverses, and even 4. So that means, and we had already done this when you're looking at groups. When you're looking at groups, we say that Z star n, Z star n, Z star n, we defined this group as a group of elements which are relatively prime to n. Elements which are relative. So every time you're doing this, you know how you define. So you define your group properly. You define it properly. So what I again want to emphasize, that the way books are written, you must not, every time you're reading a book, get to know how Z star n has been defined. Get to know how it has been defined. If it has been defined as the removal of 0 only, then not every Z star n will be a group. Not every Z star n will be a group. If it's defined as removal of 0 only, like in this case, then not every Z star n will be a group. The only time Z star n will be a group is when n is prime. When n is prime, for instance, Z star 7, which is 1, 2, 3, 4, 5, 6 will be a group. Because we've just removed 0. We've just removed 0 from this, and it's all these elements have inverses. Closure is satisfied, associativity is satisfied, and so on. So my emphasis is every time you're looking at Z star n, understand how it has been defined so that you can tell whether it's a group or not. If it's defined as removal of 0, then note that it only becomes a group if n is prime. But if it has been defined as a group consisting of elements relatively prime to n, then it will always be a group. It will always be a group. Good. So that was just again to help us recall what we've been looking at under groups. So that I know that maybe if you're reading other books or maybe reading online, sometimes because of the definition, it may confuse you because of the definitions. Because you may have seen that Z star n is always a group, and then you find that it's not a group in some instance. So if it's not a group, it means it only. Now, so let's go back to our proof. We want to show that this is a homomorphism and the ranges obtained by squaring the element. So we want to show, since we are looking at it, and that is a multiplicative groups. These are multiplicative groups. So this symbol here then means multiplication this time. It means multiplication. So we want to consider the left-hand side and then consider the right-hand side and see whether they're equal. See whether they're equal. Now, so I pick two elements. Let me pick A and B. A and B, those are the elements I'm picking from R star. Of course, they will mean 2, mean 3, 4, 5, and so on. So apply phi on the products. By this definition, the result will be the same as A times B squared. Of course, every time you square this, it will be the same as A squared times B squared. That's what you get. So I'm just using this knowledge. For instance, if I have 2 and 3, and I'm multiplying them, and then getting a square of this. So the square will be just the same as 2 squared times 3 squared, which is, of course, this will be 4 times 9, which will be that 6. Is it? Yes, it will be that 6. Or alternatively, if you want, you can just multiply these two, get 6 and square, get that 6. Now, so the left-hand side, phi of AB A times B, the same as the square of A and B, the square of this product, which is A squared times B squared. What about the left and the right hand side? Let's consider phi of A. Should be same as A squared. What about phi of B? That's B squared. Then combine these two, get A squared times B squared. So we found the left hand side as this, and the right hand side is also given as this. The two are equal, so it means phi is a homomorphism. Is a homomorphism. It means phi is a homomorphism. So it's very good to know how to these homomorphisms when you look at combining two groups, for instance. Because every time you are doing encryption and decryption, we always looking at how to improve security. And when you are dealing with the two groups, then the security is more than when you are dealing with a single group. And you can even deal with the three groups and deal with the four groups on security. Because we want something that one cannot easily decrypt. So then you're looking at, supposing you have one, you see if you have one group, somebody can easily even try brute force, try this, try that, and see which one gives you the correct answer. But if you have several groups, you complicate actually, and therefore anybody wanting to crack may not know where to begin from because of you complicated the whole thing. Now, so the following Rust program shows us how to implement a homomorphism from a set of integers to integers mod n, the one we've looked at above, example above. So I want to just implement a homomorphism from integers to integers mod n. Now, so what this is doing, this Rust program will be doing, therefore, is just to prove that something is a homomorphism, that it's what you've been given is a homomorphism. That's what I'm just trying to do using this program. So it will just be doing what we've been doing above. It can do these questions. This Rust program can do these questions. Can do this question, example 108. It can do example 108. So what I'm doing is, for instance, giving it this group, and I'm giving it this other group, and then I'm giving it the definition of phi, and then I want it to tell me whether this phi is a homomorphism. That is what the Rust program that I want to share will be doing to us. Of course, after I've shared this Rust program, we always want to customize it. You look at it and customize and add in a few things, improve it, and remove some things. So I've said it defines a trait for homomorphisms and provides a specific implementation that maps integers to their respective equivalence classes mod n, mod 6. Equivalence classes. I think that's a term I may have used it and maybe I never explained what it means. So of course, when you're looking at Zn, we're looking at elements 0, 1, 2, 3, and up to 5. And these are what we call the equivalence classes. Equivalence classes, 0, all those numbers mod 6. Or if it's mod n, all those numbers mod n, or we call equivalence classes. Equivalence classes, these elements of Zn. Those are we call equivalent. So when you meet that term, equivalence classes, does not mean a very complicated thing. It's not very complicated. It just means elements mod n. Now, so in my notes below, I'll explain what this trait homomorphism does, its work. Of course, I've said that is what defines it. Okay, at this point, I'm just defining a trait for homomorphism, and that trait, I call it T. So mapping T to itself, for instance. And then we will have a struct mod homomorphism. And of course, I132, we know what it means. We know that 32 means 32 bits, and the I means we'll be dealing with either negative or positive numbers. Of course, integers here are positive and negative. Positive and negative, and that is why I is very important. Otherwise, we would have talked of U. We would have talked of U32. U32, we know that when we talk of U32, we mean that we only be dealing with the positive numbers. But since integers will be negative, we want to deal with both negative and positive numbers. Okay, so I'll be sharing the code. We know what this symbol means. Actually, this is the remainder input mod. So when you divide it by the modulus, you divide by the modulus, the input, then divided by the modulus, what you get is what is written here. The remainder of what you get when you take the input and then divide it by the modulus is what is. So this symbol, we again understand it. Now, so this is our main function here, our main function. So in our main function, I put N, B, just to, so these are integers. So suppose I have, you see what we have this, we have mapping the integers to the integers mod 6. So I just pick any two integers here. Just pick any two. In our examples, we've been using A and B. So I want to call A to be 14 and call B to be 5. And I want to see whether 5 of 14 plus 5 will be the same as 5 of 14 plus 5 of 5. So then this code will be doing it for me. The code will be doing it for me to see whether it gets the result on the left side is the same as the result on the right side. So my A, I just call it 14, and my B, I call it 5. And remember, I'm doing it mod 6. You can always change your mode depending on the group you want to deal with. Now, so this is where the calculations will be doing. The calculations will be doing. So look at this symbol here. Actually, it's just 5. I was using Unicodes because you see, when I normally do this in Rust, for me to type it in my program that I use for making notes, when I carry the way it is as phi A plus B, my program rejects. So then I change this to a value, a symbol that my program can understand. And of course, even this one, Rust understands it. So when you run this in Rust will convert this thing to phi, to understand this as phi. And it's the same thing here. So this is the same as phi of A plus phi of B mod 6. So this is the only place that I changed that, just because of the program that I use for writing my notes. It will not accept phi directly. cannot run. It's the same thing here. Same thing here. But now, this is where the calculation is taking place. Test the homomorphism. It's just testing the homomorphism property. Phi of A plus B to see whether it gets phi of A plus phi of B. So this is a calculation. Let mapped sum be homomorphism map. So that means you are mapping this. This is the sum we are mapping, where A and B have been defined. A has been defined as 14, and B has been defined as 5 from above. So that is a mapped sum. Now it will then be doing this mapped sum mod. So this is what it's doing. So it takes A, map A. Okay, this is the right-hand side. This is the right-hand side. The map of A plus the map of B. And each of this, this A, it does it mod 6. Does it mod 6 and writes the remainder. So it takes A, divides by 6, and notes the remainder. So for instance, our A is 14. So it divides by 6. The remainder will be 2. 2 is what is written. Then plus, our B is 5. Divided by 6, the remainder is 5. So the answer we get is 7. The answer we get is 7. So that's what it's doing. That's why, that is what is happening here. Of course, I have included notes to explain that, but I just wanted to understand the symbols and how it's working. Okay, so let me just share the code first of all. You can see it, huh? Can you see my code?
Yes.
So this place that we define the traits, and then come and represent the struct. So from here, just a minute. I will explain that. I want that what it means. I've already explained what this means, what is happening there. So the input to the put, for instance, 14 divided by the modulus, in this case 6, and the remainder is what is we record. That's what that symbol means. Okay, let's run this because we want it to prove whether it's a homomorphism. And I said the Rust will understand this thing. So I just need to, can see I changed the phi. You can replace it to phi. You can just delete this part and replace by the word phi. And also this other part, replace by the word phi, and so on. I did this because of the program that I used to write my notes to not accept phi. So let's go run. Now, so it has given us some results. It has told us that phi of 14, so it was checking the right-hand side. The right-hand side, phi of 14 is 2 because it took 14 divided by 6. The remainder is 2. And then phi of 5 takes 5 divided by 6. The remainder is 5. Okay, so then those are results. What about phi of the sum. So this sum is 19. On division by 6, the remainder is 1. So the left-hand side gives us 1. What about the right-hand side? The right-hand side, we had a 2 and we had a 5. Sum them together, that is what is happening here. 2 and 5. Sum them together, you get 7. Then now divide that result by 6. The remainder is 1. So it checked for us the left-hand side, then checked for us the left-hand side. And then it can see that the two are equal. Since they're equal, it concludes and says homomorphism property is verified. Since they are the same. So that then means that phi as given to us is therefore a homomorphism. Otherwise, if it's not a homomorphism, it will have said is not. The homomorphism property is not verified. Now, so you understand what has happened. What has happened is it understands that the left-hand side, phi of A plus B should be the same as phi of A plus phi of B. So it does phi of A plus B by just summing, getting 19, and remember it was mod 6, so divided by 6, the remainder is 1. Then phi of this, phi of 14, it has done it and found it to be 2. Then phi of 5 has been done and the result was 5. Now the sum of the two is 7. That's mod 6, the remainder is again. So that is how it does. Always modify it. Modify Z. You can even have Z3 mapping to Z6 and find how you want it to. You want an element to be mapped to twice its original value, or thrice its original value, or do you want the result, the element to be mapped to A plus B? No, A plus 2, for instance. You want to map Okay, so I think it logged me out. But you can now hear, is that okay?
Yes, we can hear you, sir.
Okay. So let me share. Now, so I've included the notes to help you understand how the code came about, so that you can also customize and come up with the code and so on. This part defines the trait. A trait T defines the generic T. This trait requires implementing a method. So it's the one that will be implementing a method. Self-input T. And so this will be taking an input T and returning a value the same as T. So that's what it means by self-input T to itself. You can see this, there's this meaning that, so if the input is T, then what will be returned T? That's what it means. So what is the role of this? The role of this is that this trait will represent a function that maps elements from one set to another, as just the same way the homomorphism does. So it will be mapping elements of one set to another. But now what it's doing is this element is mapped to itself. An element T mapped to itself. That's what it self input means, a trait. Then we have this other part, strat homomorphism from Z to Z, Z6. Now, what is the role of this? It's just it's used for modulus operation. This one we use for modulus operation, and this case we are doing it mod 6. So that's why we written here modulus I132. So it is to ensure that the operations, modulus operations, are done effectively, so that if you have a result giving us a negative number, it's again handled properly. If it's giving us the operation giving us a positive number, it's again handled properly. So it's just meant to assist us do operations in modulus arithmetic. Okay, then we have this implement. We have this implement homomorphism I132 for mod homomorphism. Then we have a function, again, the same thing, itself, input to. So this element will be mapped to I132. This element, which is one I132, is mapped to another element, which is one I132. But then the input this time is reduced. The input is reduced to mod n. So that means if the input was 14, the result will be, we are doing it mod 6. We are doing it mod 6. So the result will be 2. That's what this means. That's what it means. So you have the input. You have the input, but then the input is mapped to input divided by the modulus, the remainder. You note the remainder. So for instance, the input is 14, then the output then will be 2. If the input, the output will be 5 mod 6. So you divide that 5 by 6, and then the output will be the remainder. So that's what this part means. Okay, so you'll go through the other parts again. I think this is the only part that requires the explanation. The others, you can understand them easily. You can understand that because what it remains is just the main function. The main function, of course, is where we put our A14, B14, and I've already told you what this means. This is just phi of A plus B, and this is equals to, this part is 5A and plus this other part is 5B. And I already said I use this this type of measures to ensure that my program can run when I because I copy the Rust code the way it is and then paste there. So for me to paste there, for me my code to run, it cannot run with the phi as it is. Now, so that is what we've just done. And this part says let mapped sum, let the mapped sum be the homomorphism of A plus B. This is the side. And let the mapped sum, that is now the right-hand side, No, the left-hand side, still the left-hand side. So now it wants to calculate it. Wants to calculate it, and it's telling you that we would then take let mapped. No, this is the left side. Let the mapped sum. This is the left side. It ends here. So that is 5A plus B. And this is slightly different. It's called let sum of mapped. Sum of mapped. This one was mapped sum. So sum of mapped. So what was mapped? The sum of that. What was mapped? The sum of that. Let sum of mapped. So that is what we've written here as sum 5 plus 5b. The result divide mod 6 and out the remainder. So that is what is happening in the main function. Okay, thank you. I want to stop there. I'll share the notes so that you can go through and understand that what homomorphism is, group homomorphism. And after that, we look at that example. And of course, we look at more tomorrow. Thank you.